On March 30th, 2026, at 2:47 in the morning, the Sun fired an X-1.4 solar flare, driving a coronal shockwave at 1,872 kilometers per second and a plasma cloud the size of several Earths directly at us. 5 hours and 25 minutes later, the ground broke. A 7.3 earthquake tore through Vanuatu, triggering a tsunami warning across the region. While the Pacific was still shaking, 4 more seismic zones lit up across the ring of fire, like someone was flicking switches. Now, correlation is not causation. That's the responsible thing to say. But the data sitting underneath this story is stranger than the headline, and by the end of tonight, you will understand exactly why the timing doesn't add up. Hit subscribe and stay close, because new information is still coming in. The active regions are still evolving. The ring of fire is still unsettled. And that 24-hour window that produced a monster solar flare, a major earthquake, and a Pacific tsunami warning all at once is not a story that ends cleanly. When something moves, this channel is where you hear it first. You will want to be here for that. Now, let us get into it. At 2:47 in the morning, Universal Time, on March 30th, 2026, the Sun did something it had been threatening to do for days, and nobody was quite ready for it. Active Region 4405, a magnetically unstable patch of the Sun's surface that scientists classify as beta-gamma in configuration, which is essentially the solar physics equivalent of a loaded gun sitting on a table, unleashed an X-1.4 solar flare. Now, if you're not familiar with the X-class designation, here's all you need to know. It sits at the top of the flare intensity scale. The scale goes A, B, C, M, X, and within X-class, the numbers keep climbing. An X-1.4 is not the largest flare the Sun has ever produced. Not even close. But what makes this one worth your full attention has nothing to do with the number alone. It has everything to do with the timing, the direction, and what was already happening before it fired. The flare itself produced what's called a Type 2 radio burst. That's a specific kind of electromagnetic signature that only appears when a coronal shock wave is traveling outward through the solar atmosphere. It's a sonic boom in plasma, and the shock speed clocked in at approximately 1,872 kilometers per second. To give you a sense of what that means physically, a bullet travels roughly 1 kilometer per second. This wave was moving at nearly 2,000 times that, and it was headed, at least in part, toward Earth. Alongside the radio burst, instruments aboard the SOHO satellite, that's the Solar and Heliospheric Observatory, essentially one of our best eyes on the Sun, captured what's called a partial halo coronal mass ejection, a CME, and this one had an Earth-directed component. A CME, for anyone who hasn't heard the term before, is essentially a cloud of solar plasma carrying a frozen magnetic field, flung off the Sun at extraordinary speeds. It doesn't travel at the speed of light the way the flare's radiation does. It lumbers. It takes between 1 and 3 days to cross the roughly 150 million kilometers between the Sun and Earth, which means that when the CME left the Sun on March 30th, it had an appointment on Earth's doorstep that we could mark on a calendar. The problem is, we didn't know exactly how hard it was going to knock. The radio environment on Earth's sunlit side degraded almost immediately after the flare peaked. NOAA classified it as an R3 radio blackout. That's a strong blackout level on a 5-point scale, affecting high-frequency communication across the hemisphere that was facing the Sun at the time. The 10-centimeter radio flux, which scientists call the 10-flare measurement and use as a proxy for solar activity intensity, spiked to around 1,800 solar flux units. That's the kind of number that makes space weather operators sit up straighter in their chairs. Now, here's something that's worth pausing on, because it speaks to the nature of how these events unfold. Active Region 4405 had already been producing M-class flares in the days prior. M-class flares are one tier below X-class. Still significant, still energetic, but manageable. The region was being watched. It was flagged as unstable. But the forecast models did not predict it would escalate to X level. And then it did. That gap between what the models expect and what the sun actually does is one of the most important and humbling aspects of space weather science. We are watching a system so large and so complex that even our best predictive tools sometimes just watch it happen alongside the rest of us. There's a detail worth layering in here, because context matters. The launch window for Artemis 2, NASA's first crewed mission to deep space since the Apollo era, carrying 4 astronauts around the moon, was sitting at April 1st, 2026, 24 hours after the CME left the sun. We'll come back to what that means. For now, just hold that thought. The important clarification to make right here, before we go any further, is this. An X-class flare is not an apocalypse indicator. It is an energy classification. The sun produces them regularly, especially near solar maximum, which is where we currently are in solar cycle 25. They do not end civilization. They do not automatically trigger disasters. What they do is inject an enormous amount of energy and electromagnetic disturbance into the near-Earth environment, and depending on what that environment already looks like when the energy arrives, the effects can range from minor to genuinely disruptive. And the environment, as we're about to get into, was already in a very unusual state. The story of this flare is not simply that it happened. The story is what it happened into, because the sun had not been quiet in the days before March 30th. Not even close. The electron environment around Earth, the outer radiation belt, specifically, had been running hot for 9 consecutive days. 9 days of 2 mega-electron-volt electron flux above the alert threshold of 1,000 particle flux units. And at its peak, that flux reached approximately 3,755 particle flux units. That's not a brief spike. That's a sustained, elevated radiation environment wrapping the planet before the flare even fired. Here's why that matters more than it might sound. The outer radiation belt is a zone of high-energy electrons that encircles Earth at altitudes between roughly 13,000 and 50,000 kilometers. Satellites in geosynchronous orbit, the ones running your weather forecasts, GPS signals, and communications networks, sit right in the middle of that zone. When the electron flux climbs and stays elevated, the risk of surface charging on those satellites increases substantially. Charging events can cause phantom commands, bit flips in onboard computers, and in extreme cases, permanent damage to components. The satellites don't announce when this is happening. They just start behaving strangely, and engineers have to diagnose the cause after the fact. So when the flare fired and the CME launched, it wasn't hitting a neutral system. It was hitting a system that had already been absorbing 9 days of elevated electron bombardment. Think about it like this. Imagine a power grid running at 90% capacity during a summer heat wave. Then a lightning storm rolls in on top of it. The storm alone might be manageable, but the combination, hitting a grid already under stress, is where things get interesting. That was the space environment around Earth on the morning of March 30th. Electrically stressed, preloaded, and a CME inbound. A coronal whole high-speed stream had also been influencing the solar wind in the days prior, pushing solar wind speeds to around 450 kilometers per second. And the interplanetary magnetic field, the IMF, which is essentially the sun's magnetic influence stretched across the solar system, had been showing what scientists call BZ instability. The BZ component of the IMF is the one that matters most for Earth. When it points southward, it connects with Earth's magnetic field in a way that opens a door, allowing solar energy to pour into the magnetosphere. When it points northward, that door closes. The problem is that the BZ direction of an incoming CME can't be reliably measured until the cloud is about 15 to 60 minutes from Earth. We have no way of reading it from a distance. We find out when it arrives, which means NOAA's Space Weather Prediction Center was working with incomplete information when it issued its forecast on March 30th. A G2 geomagnetic storm watch, moderate, with possible brief excursions to G3, which is strong. KP index, the global measure of geomagnetic disturbance, running on a scale from 0 to 9, was forecast to peak somewhere between 5.6 and 5.7. That's not a record-breaking number, but it was high enough to put aurora forecasting agencies on notice that people in New York State, Washington State, and similar latitudes might actually see the northern lights. Not a guarantee, not a spectacle, but a possibility that hadn't existed the day before. And here's the thing about equinox timing that most people don't know. There's a real, documented phenomenon called the Russell-McFerrin effect. It's named after the two researchers who described it in 1973, and it explains why geomagnetic storms near the spring and fall equinoxes tend to be more intense than storms of equivalent solar input at other times of year. It has to do with the geometry of how Earth's magnetic field aligns with the Sun's magnetic field during the equinoxes, making it easier for solar energy to couple into the magnetosphere. Earth had just passed the March equinox. We were still inside the enhanced coupling window, which means the CME, whenever it arrived, was arriving at a favorable angle for impact. The forecast said moderate. The system was already behaving like more. And the question that was sitting quietly in the background of every space weather dashboard on the planet was whether the CME's BZ component would flip southward upon arrival, and how long it would stay that way. That single variable, unknowable in advance, is what separates a memorable light show from a genuinely disruptive geomagnetic storm. And somewhere between 1 and 2 days from March 30th, we were going to find out which one this was. But before the CME arrived, the Earth did something of its own. 5 hours and 57 minutes after the X 1.4 flare peaked at the Sun, at 8:44 Universal Time, on March 30th, 2026, the ground beneath the island chain of Vanuatu tore apart. Magnitude 7.3. Depth 121 kilometers. The earthquake struck near Luganville, the second largest city in Vanuatu, a small island nation sitting in the southwestern Pacific Ocean, on one of the most geologically active boundaries on the planet. A magnitude 7.3 is classified as a strong major earthquake. It's the kind of number that, wherever it occurs on land, causes serious damage. Wherever it occurs offshore near populated coastlines, it triggers an immediate and extremely serious question: is a tsunami coming? The answer in this case was, we don't know yet, but we're not taking chances. A tsunami warning was issued relatively quickly after the event, and that decision was based primarily on the magnitude, not the depth alone. Here's why depth matters in earthquake science. This was what seismologists call an intermediate focus event. The rupture occurred within a subducting tectonic plate, the Pacific Plate, in this case, grinding beneath the Australian plate along the New Hebrides subduction zone, at a depth that puts the source of the energy well below the seafloor surface. Deep earthquakes, generally speaking, produce less violent surface rupture than shallow ones. The seafloor displacement that drives tsunamis is a function of how dramatically and quickly the ocean bottom moves. A rupture at 121 kilometers depth has a significant cushion of rock between the source and the sea surface. But the key word there is generally. Magnitude 7.3 events can still disturb the water column enough to generate waves, and the uncertainty in the first minutes after a major offshore earthquake is enormous. You don't wait for certainty before issuing a warning. You issue the warning, and then refine as data comes in. What made this event particularly notable in terms of seismic context was not just what happened in March of 2026, but what had happened in the 4 months before it. Vanuatu had already been struck by another magnitude 7+ earthquake in the same region within that window. That's a cluster. The New Hebrides subduction zone is one of the fastest converging tectonic boundaries on Earth, with the plates moving toward each other at rates that geologists describe as extreme. This is not a quiet corner of the planet, but 2 M7+ events in 4 months is a concentration of energy release that seismologists take note of, even if it doesn't automatically signal something larger is coming. Aftershocks from the March 30th event began registering almost immediately, with M5+ tremors rippling outward from the main shock in the hours that followed. What happened next, though, is what starts to make the seismic picture on March 30th look like something more than a single regional event. Because Vanuatu was not the only place on Earth that was moving. Zoom out to the full global seismic map for that 24-hour window, and something immediately catches the eye. In Japan's Ryukyu Islands, a rapid-fire swarm of M4 and M5 earthquakes had been clustering in a short time frame, the kind of tight grouping that seismologists describe as spatially and temporally concentrated. Tonga, which had been struck by a magnitude 7.5 just days earlier, was still generating significant aftershocks in the M5 range, keeping that region on alert. Off the coast of Nicaragua, an M5.4 subduction event fired in the offshore trench, the kind of quiet, routine Pacific margin activity that would barely make headlines on any other week. And off El Salvador, a paired event in the same trench system registered, the two events behaving in the way that twin ruptures sometimes do along connected fault segments. Then there was Puerto Rico, where a shallow earthquake along the Caribbean plate boundary added another data point to what was becoming a genuinely unusual-looking global seismic snapshot. Now, here is where intellectual honesty has to step in, and this is important, so stay with me, because the Ring of Fire is not a metaphor. It is a real, continuous, interconnected network of subduction zones, transform faults, and volcanic arcs that encircles the Pacific Ocean basin and accounts for roughly 70 to 90% of the world's earthquakes by volume. This system is always active. Always. On any given day, there are dozens of earthquakes registering somewhere along its arc. A magnitude 4 or 5 event in Japan, an aftershock sequence in Tonga, offshore activity near Central America. These are baseline occurrences. They are not, on their own, extraordinary. What human perception does with them, however, is a different story entirely. When you have a major earthquake in Vanuatu, a solar flare, a CME, a tsunami warning, and then you pull up the global seismic map and see that 4 other zones are also lighting up, your brain does something that evolution programmed it to do. It looks for the common cause. It tries to build the story. It compresses the timeline and finds the pattern. And that compression, that urge to unify unrelated events under a single explanatory umbrella, is one of the most powerful cognitive biases we carry. We'll come back to that in detail later. For now, the relevant scientific framing is this. Seismologists use a concept called distributed stress release to describe how tectonic energy moves through the crust over time. When a large earthquake occurs, it changes the stress distribution on nearby faults, which can either promote or inhibit future events. But nearby, in tectonic terms, is relative. The Vanuatu event and the Ryukyu swarm are separated by thousands of kilometers of ocean floor. The mechanisms driving them are distinct. The Pacific plate is enormous, the largest tectonic plate on Earth, and the idea that a rupture in its southern edge would instantaneously influence behavior in its northwestern corner is not supported by the timescales of stress transfer, which move at the speed of seismic waves, not at the speed of a single catastrophic event. And yet, there is a documented historical observation, not a mechanism, just an observation, that weeks of multi-zone seismic clustering have appeared before during periods of elevated solar activity. This is not a controlled study. The dataset is complicated by the fact that we've only had reliable global seismic monitoring for a few decades. The statistics are messy, but the pattern shows up in the literature often enough that researchers have not been able to dismiss it entirely, even if they also cannot explain it. There is no confirmed physical coupling between solar events and tectonic systems. The electromagnetic fields generated by geomagnetic storms are vanishingly small compared to the forces inside the Earth. Piezo-magnetic effects, the idea that changing magnetic fields could influence the piezoelectric properties of certain crustal rocks, remain theoretical and extremely controversial. No credible mechanism has been accepted by mainstream geoscience. But here is the timeline that nobody can simply wave away with a sentence. At 3:19 Universal Time on March 30th, the X1.4 flare peaked. At 8:44 Universal Time on March 30th, the magnitude 7.3 earthquake struck Vanuatu. That is a separation of 5 hours and 25 minutes. The CME had not yet reached Earth. The geomagnetic storm had not yet begun. The solar event that would have the strongest potential influence on the ground, if any such mechanism exists, hadn't even delivered its energy yet. That timing detail matters enormously, and it is something that a lot of the online discourse around these events tends to get quietly wrong. The correlation being drawn between the flare and the earthquake requires, at minimum, a mechanism that acts on a 5-hour timescale, faster than the CME transit time, faster than the geomagnetic storm. The electromagnetic radiation from the flare does reach Earth in 8 minutes, but that radiation, the X-ray and ultraviolet burst that caused the radio blackout, is not the kind of field disturbance that anyone has proposed as a tectonic trigger. It's ionospheric, not lithospheric. It affects the upper atmosphere, not the crust. So what we have is not a connection. What we have is a timeline. And what the timeline tells us is that the sun fired, the earth shook, and the gap between those two events is the whole problem. Close enough to feel meaningful, but just far enough apart, and just mechanistically disconnected enough that science cannot build a bridge between them. At least not yet. Whether the timing is a coincidence of a busy, active planetary system, or whether it is pointing at something we don't yet have the instruments to measure, that question remains genuinely open. And the Earth, meanwhile, was not finished moving. There is a particular kind of unease that sets in when you realize that multiple large, independent systems are running at high intensity simultaneously, and that you're standing on one of them, not watching from a distance, not reading about it the next morning, standing on it, in real time, while the data comes in. That is the specific quality of discomfort that March 30th, 2026 produced for anyone paying close attention. And the more carefully you looked at the structure of what was happening, the more that discomfort deepened, not because any single event was unprecedented, but because of the architecture of their overlap. Let's lay out exactly what was operating in parallel on March 30th, because the structure of it is worth seeing clearly and completely before we start drawing any conclusions from it. The solar system, meaning the space weather environment, not the planets, was producing 3 overlapping drivers at once. An X1.4 flare had fired and sent a shockwave through the solar corona at nearly 2,000 kilometers per second. A partial halo coronal mass ejection was in transit toward Earth, carrying a magnetic field whose critical southward orientation was still unknown and would remain unknown until it was approximately 15 to 60 minutes from arrival. And the electron environment around the planet had been running above alert thresholds for 9 consecutive days, with a peak flux level nearly 4 times the alert threshold of 1,000 particle flux units. 3 drivers, all active simultaneously, none of them individually record-breaking. Together, they were producing a space weather environment that the models were having genuine difficulty characterizing with confidence. The geophysical system, entirely separately, was producing its own multi-signal output with its own internal structure. A magnitude 7.3 had struck Vanuatu at 121 kilometers depth and triggered a tsunami warning across the southwestern Pacific. An aftershock sequence from the magnitude 7.5 that had struck Tonga just days earlier was still generating M5+ events and keeping that region on alert. A rapid-fire swarm in Japan's Ryukyu Islands was clustering in a way that seismologists describe as spatially and temporally concentrated, multiple moderate events in a short window, in a confined geographic area. Twin events had fired off the coasts of Nicaragua and El Salvador along the same Central American subduction system, the kind of paired behavior that suggests stress transfer along connected fault segments. And a shallow Caribbean plate boundary earthquake had added one more signal to a map that was already looking unusually active. 5 distinct seismic zones, all generating significant signals inside the same 24-hour window. All of them on the Ring of Fire. All of them independent. All of them real. And then there was a third system, the human one, which is perhaps the most underappreciated dimension of the March 30th story, because it is the one that transforms the event from a remarkable natural coincidence into something with direct, immediate operational consequences. Artemis II was sitting on the launch pad at Kennedy Space Center, scheduled to carry 4 astronauts, Reed Wiseman, Victor Glover, Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen, on the first crewed mission beyond low Earth orbit since Apollo 17 in 1972. That was 53 years of crewed spaceflight confined to the relative shelter of low Earth orbit inside the protection of Earth's magnetic field. Artemis II was going to take human beings back out through the Van Allen belts, past the magnetosphere's protective boundary, into the genuine deep space radiation environment. Launch window, April 1st, 2026, approximately 24 hours after the CME's estimated arrival at Earth. These are not 3 separate news stories running independently in parallel columns. They are 3 high-stakes systems, all elevated simultaneously to unusual activity levels, all converging on the same narrow, unforgiving window of time. Now let's be precise about what the Artemis II mission actually means in terms of radiation exposure, because this is not a theoretical risk being discussed in an academic paper. It is a concrete engineering problem that NASA has been actively modeling for years, and the events of March 30th brought it into sharp, immediate, operational focus. The Van Allen radiation belts are 2 concentric zones of trapped charged particles that encircle Earth at altitudes between roughly 1,000 and 60,000 kilometers. The inner belt is dominated by high-energy protons, energetic enough to penetrate spacecraft walls and damage biological tissue. The outer belt, the one that had been running at elevated flux levels for 9 consecutive days, is dominated by energetic electrons. These electrons are less immediately dangerous to human tissue than the inner belt protons, but they are highly damaging to spacecraft electronics and can contribute meaningfully to crew radiation dose over the course of a transit. Any spacecraft traveling from low Earth orbit outward to lunar distance has to pass through both of these belts. There is no trajectory that avoids them. You go through or you don't go. The Orion spacecraft carries radiation shielding specifically designed to reduce crew exposure during the belt transit. But shielding in spacecraft design is always a compromise negotiated against mass. You cannot build an infinitely thick radiation barrier around 4 astronauts without making the rocket physically incapable of lifting the vehicle off the ground. Every gram of shielding added is a gram taken from somewhere else. The design that NASA settled on balances acceptable crew radiation risk against mission capability under nominal space weather conditions. The key phrase there is nominal. Under elevated conditions, a pre-energized outer belt that had been running hot for over a week, a CME that had just delivered a significant geomagnetic storm hours before launch, lingering elevated particle flux still decaying through the belt system, the calculation shifts, not automatically to the point of mission cancellation, but absolutely to the point where NASA's Space Radiation Analysis Group, the team known as SRAG, would be running continuous, real-time, hour-by-hour assessments of the radiation environment and whether the crew's projected dose remained within acceptable mission parameters. Here is the specific detail that makes the timing genuinely uncomfortable, rather than merely inconvenient. Even when a geomagnetic storm begins and then ends, the radiation environment in the outer belt does not reset cleanly the way a circuit breaker does when you flip it back. The energetic electrons injected into the outer belt during a geomagnetic storm become trapped in the Earth's magnetic field and decay slowly over a period of days to weeks, depending on the intensity of the storm and the state of the magnetosphere. A CME that hits Earth on March 31st and drives a G2 or G3 geomagnetic storm does not produce a clean radiation environment on April 1st. It produces a recovering environment, an environment still elevated above baseline, still trending downward, but not yet back to the levels that pre-storm models were calibrated against. And recovering is emphatically not the same as safe. The question that SRAG was going to have to answer on the morning of April 1st was not whether the storm was technically over. It was whether the particle inventory remaining in the belt system had decayed sufficiently to keep the crew's projected radiation dose inside the mission's acceptable limits for the full duration of the transit. That assessment was going to be made in real time, with a crew on board, with a launch clock counting down, with mission managers waiting for a go or no-go call. And no model built before the CME arrived could pre-answer it, because the model's inputs, the actual storm intensity, the actual BZ orientation, the actual injection of particles into the belt, were not known until it happened. The broader context that frames all of this is solar cycle 25, which had been behaving in ways that surprised even the forecasters who had built their careers around predicting it. Solar cycles run approximately 11 years from minimum activity to maximum and back down to minimum again. Cycle 25, which officially began around December of 2019, had been tracking significantly above the official predicted intensity for most of its ascending phase. The initial consensus forecast had called for an average cycle, unremarkable by historical standards. The sun had other ideas. By the time 2024 and 2025 rolled around, Cycle 25 was producing flare rates and active region complexity that exceeded the median forecast by a measurable margin. The solar maximum, the peak period of sunspot number and eruptive activity within the cycle, was estimated to be occurring somewhere in the 2024 to 2026 window, with the inherent uncertainty that comes from the fact that you can only identify a solar maximum with confidence after the activity has started declining. You cannot stand at the peak and know you are at the peak in real time. You can only suspect it. Active region 4405 was not an anomaly within this context. It was a product of it, a direct expression of a cycle running hotter than predicted, generating magnetically complex regions with the kind of beta-gamma configuration that produces X-class events. And as of late March 30th, that region was still rotating across the solar disk. The sun rotates once every approximately 27 days as observed from Earth's moving vantage point, when an active region sits near the eastern limb of the solar disk. The left edge as we observe it from Earth, coronal mass ejections it produces tend to be poorly aimed at our planet, deflected to one side of the Sun-Earth line. As a region rotates toward the center of the disk, toward what solar physicists call the central meridian, it becomes progressively more geo-effective. Its eruptions point more and more directly at Earth. Its CMS, if produced, travel more squarely down the Sun-Earth line and arrive with higher impact probability and potentially greater geomagnetic effect. Active Region 4405 was approaching that central meridian position as March 30th ended, which meant that in the days immediately following the X-1.4 flare, if the region fired again, and the magnetic complexity that produced the first flare had not suddenly resolved, the geometric conditions for Earth impact would be improving with every hour of solar rotation. The short-term flare probability models do not collapse to zero after an active region produces an X-class event. In fact, large flares sometimes appear to trigger what solar physicists describe as sympathetic activity, eruptions in other active regions on the solar disk, driven either by the propagating shockwave moving through the corona from the initial eruption, or by magnetic connectivity along large-scale coronal field lines that link distant regions of the solar surface. Active Region 4405 was not operating in isolation on the solar disk. There were other magnetically complex regions present. Whether any of them would respond to the March 30th eruption in the hours and days that followed was a question that nobody sitting on Earth at the end of that day could answer with any confidence. This is the defining characteristic of solar maximum that distinguishes it operationally from solar minimum, and it is something that does not always come through clearly in the public communication around space weather. It is not simply that the flares are larger or more frequent, though they are both. It is that the entire system is running with more simultaneous complexity, more active regions, more magnetic stress distributed across the disk, more loaded configurations capable of erupting on short timescales. Pulling one trigger at solar maximum does not simply discharge one gun. It rattles the table that all the guns are sitting on. The X-1.4 event may have been the conclusion of Region 4405's story for this solar rotation. Or it may have been the opening act of something longer. Both possibilities sat on the table with equal plausibility as the CME crossed the inner solar system and the launch clock at Kennedy Space Center counted down toward April 1st. And there was only one way to find out which one it was. The same way you always find out on this frontier. You watch, you wait, and you hope the models are close enough to right that the gap between what they predict and what actually happens stays within a range that your systems and your crew can survive. Let's talk about the thing that nobody in mainstream science wants to spend too much time on, and also the thing that everyone who watched March 30th unfold in real time was thinking about, whether they said it out loud or not. Because there is a conversation happening in the margins of the scientific literature that rarely makes it into press releases or university announcements. It lives in footnotes and caveats and the careful language of researchers who know exactly how their peers will react if they push too hard on a conclusion that the data doesn't fully support yet. And on March 30th, 2026, that conversation moved from the margins to the center, whether the people having it wanted it to or not. There is a body of published scientific literature, peer-reviewed, published in journals, authored by credentialed researchers, that examines statistical correlations between solar activity and seismic events on Earth. This is not fringe material from a YouTube comment section. This is real science, done carefully, with all the appropriate caveats attached. A 2015 study published in the Journal of Atmospheric and Solar Terrestrial Physics found weak but statistically non-negligible correlations between geomagnetic storm intensity and global seismic frequency in certain frequency bands. A separate line of research has looked specifically at the timing relationship between CME impacts and M5+ earthquake occurrences in the following 24 to 48 hours. The results are inconclusive. Some studies find signals, others find nothing. The meta-analysis of the meta-analyses is, itself, unresolved. And that unresolved quality, that persistent, stubborn refusal of the data to either confirm or fully deny the connection, is precisely what keeps serious researchers returning to the question, even when the professional incentives push them away from it. The critical distinction that science insists on drawing, and it is a fair distinction, one worth understanding clearly, is the one between correlation and causation. Correlation means that two things tend to happen near each other in time or space more often than you would expect by pure chance. Causation means that one thing is physically producing the other through an identifiable, testable, reproducible mechanism. You can have correlation without causation. You can observe a pattern in the data for decades without being able to explain the physics behind it. And the solar seismic literature is, at the moment, firmly in the correlation without mechanism category. That doesn't mean the correlation is meaningless. It means we don't yet know what it means. There is a significant difference between those two things, and collapsing that difference in either direction, either dismissing the correlation entirely or declaring it proof of causation, is where intellectual honesty breaks down. Here's the specific problem that the physics presents. For a solar event to trigger an earthquake, some form of energy or force from the sun would need to couple into the solid Earth, into the crust and mantle where tectonic stress accumulates over decades and centuries in a way that is strong enough to advance the failure of a fault that was already approaching its critical stress threshold. Not create the stress from scratch. Just nudge a system that is already near its breaking point over the edge, slightly earlier than it would have failed on its own. The candidates that researchers have considered are varied and genuinely interesting. Variations in atmospheric and ionospheric electrical fields that might couple downward through the ground. Piezomagnetic effects in crustal rocks that contain iron-bearing minerals, where changing magnetic fields alter the mechanical stress state of the rock itself. Variations in the magnetotelluric current systems, large-scale electrical currents that flow through the crust in response to geomagnetic disturbances, which might concentrate stress along conductive fault zones. Thermal or electrical loading of fault zones near the surface during periods of elevated geomagnetic activity. Each of these mechanisms is physically real in the sense that the underlying phenomena exist. The problem is quantitative. The energy delivered by even a severe geomagnetic storm to the solid Earth is many orders of magnitude smaller than the energy stored in a major tectonic fault system. You are comparing the push of a breath to the tension in a cable under 10,000 tons of load. The math, as currently constructed, does not work. And until someone finds a mechanism that closes that energy gap, the scientific community's skepticism is not unreasonable. Which brings us back to March 30th and the 5-hour, 25-minute gap that sits at the center of this story, like a splinter that nobody can quite remove. The CME had not arrived. The geomagnetic storm had not started. Whatever solar energy had reached Earth by the time the Vanuatu earthquake struck was limited to the X-ray and ultraviolet radiation from the flare. Photons, not particles, not fields, not plasma clouds carrying frozen magnetic fields. High-energy photons from a solar flare are absorbed in the upper atmosphere, in the ionosphere, at altitudes of hundreds of kilometers above the surface. They do not penetrate to the crust. They do not reach the fault zones where tectonic stress lives. The earthquake cannot, by any currently proposed mechanism, have been triggered by the flare in that 5-hour window. And that is not a dismissal of the question. That is the question becoming sharper and more uncomfortable. Because if you are going to take the solar seismic correlation seriously, and the published literature gives you at least some reason to consider it, then the 5-hour gap forces you toward a much more speculative and much harder to test hypothesis. The hypothesis that something acts before the CME arrives. Some precursor disturbance in the solar wind, some shift in the interplanetary magnetic field, some change in the particle environment that was already altering the near-Earth electromagnetic system in the hours before the main event. The 9 days of elevated electron flux suddenly looks different in this framing, not just as a satellite hazard, but as a possible indicator that the system had already been perturbed, already preloaded, already shifted away from baseline, in ways that our current instrumentation captures only partially. That is a much more speculative line of reasoning, but it is the line the data pushes you toward, if you follow it honestly rather than stopping at the comfortable disclaimer. The honest position, which is also the scientifically correct position, is this: we cannot explain the timing. We can observe it. We can note that it falls within the pattern that appears in the literature. We can acknowledge that the gap between the flare peak and the earthquake is suspiciously small, without being close enough to implicate any of the obvious physical mechanisms. And then we have to sit with the discomfort of not having an answer. That discomfort, by the way, is what science actually feels like from the inside when it is being done properly. It does not feel like certainty. It feels exactly like this. Now let's talk about why March 30th felt so overwhelming to so many people who were watching it in real time. Because the psychological dimension of this story is just as real as the physical one, and in some ways considerably more important for understanding how we process events like this. Human brains are pattern detection engines. This is not a flaw or a weakness. It is the reason we survived long enough to build telescopes and seismographs and spacecraft. The ability to notice when multiple signals are arriving simultaneously and to hypothesize a common cause has been one of the most powerful adaptive tools in our evolutionary history. Most of the time, when multiple threats appear at once, they do share a cause. A predator in the grass makes multiple sounds and disturbs multiple blades simultaneously. You are designed to connect those signals into a single explanation. The problem is that this instinct does not come with an off switch calibrated for planetary scale geophysics. The brain applies the same pattern detection heuristic to a solar flare and a Pacific earthquake that it applies to rustling grass, and the result is a feeling of connection that the physics has not yet earned. There is a concept in cognitive psychology, sometimes described as temporal compression, the tendency for humans to perceive events that are reported close together in time as being causally connected, even when the actual mechanisms linking them are absent or unconfirmed. When you receive 5 high-stakes alerts inside 4 hours, flare detected, earthquake, tsunami warning, aftershocks continuing, new seismic swarm activating, your nervous system does not evaluate each one independently and dispassionately. It stacks them. It builds a tower out of them, and a tower of 5 alerts feels categorically, qualitatively different from any single alert, even if each individual item is within the range of normal planetary behavior. The experience of receiving all 5 in rapid succession creates what you might call a multi-domain salience bias, the overwhelming sense that something larger, something connecting all of these domains simultaneously, must be responsible for all of it. And that sense, that feeling, is not evidence, but it is also not nothing. It is telling you that your threat detection system is fully engaged. The question is whether it is detecting a real unified threat or constructing one from the coincidental overlap of independent systems. Social media and algorithmic news feeds make this significantly worse in ways that are worth being explicit about. The algorithm does not curate for physical relatedness. It does not organize your feed according to whether events share a causal mechanism. It curates for engagement, for emotional intensity, for the feeling of stakes. And 5 simultaneous high-stakes events spanning space weather and Pacific geology is maximum engagement content by any algorithmic measure. The feeds collapse all the temporal and physical distance between events. The posts do not say that these 5 events occurred across 9 hours in 3 different tectonic systems, with no confirmed physical connectivity between them. The posts say the sun just fired, the earth just broke, and something about all of this feels deeply, fundamentally wrong. And here is the thing, they are not lying. That feeling is real. The events are real. The timing is genuinely unusual. It is just not, on its own, evidence of a physical connection. And the gap between a real feeling and physical evidence is exactly where the most important thinking needs to happen. There is a useful historical parallel here that grounds all of this in something we can look back on with more distance. In 2011, the Tohoku earthquake and tsunami struck Japan in March, a magnitude 9 event, one of the 5 largest earthquakes ever recorded by modern seismology. Approximately 3 weeks later, a significant geomagnetic storm struck Earth during the ascending phase of solar cycle 24. Online discourse in the weeks following the earthquake was saturated with solar seismic correlation claims. The timing felt significant. The events were both genuinely enormous. Researchers subsequently analyzed the relationship carefully and found no statistically significant connection specific to that sequence. The clustering of global seismic activity in early 2011 was real, but it was driven by post-Tohoku stress redistribution in the Pacific Basin, the main shock loading and unloading nearby fault segments, as large earthquakes always do. The solar activity was part of the cycle's normal progression. They were concurrent. They were not connected, but the perception of connection was powerful and persistent for months afterward, because the human brain finds the discomfort of an unexplained coincidence significantly harder to tolerate than even an incorrect explanation. So where does all of this leave us? Standing at the end of March 30th, 2026, with a flare in the data, an earthquake in the seismic record, a tsunami warning in the Pacific, and a CME still in transit. It leaves us with a set of genuinely unresolved questions that intellectual honesty requires naming clearly, rather than either dismissing or sensationalizing. Whether Region 4405 produced a follow-on eruption in the subsequent days, one potentially more geo-effective given its improving geometry towards central meridian, was unknown. Whether the Vanuatu rupture zone had finished releasing its accumulated stress, or whether it was in the early stages of a longer sequence, was unknown. Whether the CME's BZ component would flip southward on arrival and drive a storm exceeding the G3 forecast was unknown. Whether the Artemis 2 crew would launch on April 1st into a recovering but still elevated radiation environment, or whether NOAA's real-time assessment would call for a hold, was unknown. What space weather forecasting genuinely cannot do at the current state of the art is predict the outer boundary of variability with confidence. The models are built on averages. They capture the median behavior of systems that are, at their extremes, not median systems. The combination of a CME arriving into a 9-day pre-energized electron environment during a post-equinox enhanced coupling window with a crewed deep space mission on the pad for the following morning, in the same window as a second major earthquake, in 4 months on the same island chain. That combination puts the system into the tail of the distribution, where the models have the least historical data and the least predictive confidence. And tails are where the interesting things happen. The uncertainty, not the flare, not the earthquake, not any individual event, is the actual story of March 30th. What that day revealed is not that the sun and the earth are coordinating against us. There is no intelligence behind the timing. There is no conspiracy operating at the scale of stellar physics. What it revealed is something quieter, and in some ways more unsettling than a conspiracy. It revealed that we live on a geologically active planet orbiting a magnetically volatile star, and that our civilization, its satellite networks, its crewed space programs, its undersea cables, its power infrastructure, is increasingly embedded in the behavior of both of those systems simultaneously, and neither the sun nor the earth consulted us before deciding to have an unusually busy week. The question March 30th leaves in the air is not whether the sun caused the earthquake. The physics says it did not. The question is, what happens to a civilization that has threaded its most critical infrastructure through the space environment and the tectonic margins and the launch windows of missions carrying human beings, when all 3 of those systems run hot at once, and when the honest answer from every monitoring agency on the planet is, we see it. We are watching it in real time. and we cannot tell you with certainty what comes next. That is not a failure of science. That is what the frontier actually looks like. And the frontier, as of March 30th, 2026, was a very crowded and very unsettled place. Nothing was breaking physics. But everything was testing how we understand timing across systems that do not wait for each other. And the waiting, the watching, the sitting with the not knowing, that part had only just begun.